Let's go to liquid 1233. Remove subfolders from the file system. It gives us a string array folder, and we need to remove all of the subfolders in these folders and return a list of string which contains only the parent folder. Um, so the order does not matter. Let's look at the example. We'll say we have A folder A and also an A/B. So that means there is a subfolder on the A. And also there is /C/D. And there is /C/D/E, right? So that means there is an E on the D. And there is a /C/F. So we need to keep this. But we need to remove this and this, right? The thing is that if there is a parent folder exists, then we need to remove its children. A parent folder exists in the folders list in this array, then we'll remove the children. So for example, if there is a C here, /C, then all of this should be removed and keep only this. So how can we do this question? Intuitively, for this kind of question, we can thinking about this kind of folder. Let's talk about the first method. This folder is in we know this file system, Linux file system is like a tree structure, right? So we thinking about we can just insert this charts and trees, right? But for this kind of folder, how can we use this kind of tree? Is that we are going to use a map. The key will be the string, which will be the folder current folder name, right? And for every node, right? Every child node, there is children, which we use a map to store its children. The key will be the children's folder, and the value will be the children's child node. And when we insert those kind of folders, right? So if just insert like a child tree, right? So when we finish, just put is end or is folder, a flag here, right? And if we are able to put a is end flag, then we can add this kind of path to our result. And during our insertion, if we, for example, in our path, we met a node which already has its end, right? That means there is path which have shared the same from root to this node already exists, right? So that means this will be its sub node. In this case, what we'll need to keep? We'll keep this part and abandon this, skip this, right? So we need to make sure the short path is insert earlier. So what we want is that we compose a chart tree and we sort this folder by its length, right? And then insert. So that if we met, this is if we insert a path, in the path we see there is a is end, right? We are going to just abandon this insertion. So this will be one of the most straightforward way we can think about. We can write code for these implementations quickly, and then we'll talk about some other method. Class char node we're going to use map string char node we call children, right? And we can have a Boolean flag is folder in public node. Sometimes we can have a string to store this kind of channel. What's the current folder name, right? But for this one, we don't even need to have this. So we're going to have children equals new node, right? Then what we do is that we can have node root equals new node, right? And when we can create a insert method, we can also have the result list as insert new array list. And we're going to have a mm, we are going to have a um, insert, right? We are going to for we need arrays sort user folder, and we're going to implement this kind of insert method. We can do this for every string um, f in folder. Just insert and result as folder return results. So to implement this is that the code is private void insert. Going to have a list of string results, and we are going to have a string called dir. So we'll have child node current equals root, and let's split this dir into dirs equals dir split. So then what we do is that for int I equals 1, I smaller than the thing is that because the first one is empty, right? So we I smaller equal to dir dot length plus plus. So what we do is that string for the name, right? Because dir then what we do is that if current is folder, right? Is folder that means we for our dir we haven't finish our whole path, but we see a parent node is already a folder. That means current one is a child. We just return, right? And I will say if when we insert if current children doesn't contains key, right? Contains key for the name, then we're going to create have current children add this key put this folder new child node, and we'll have a current children get for the name. And in the end, if after insert, the whole path go through the whole path, we didn't find in its parent nodes any is folder. That means it's not for this folder. It's not contained by other folder. Then we can have flag here is folder equals true, and the result add yeah, right. So this will be the char solution. New hash map. Okay, doing like this, we'll see for every let's analysis the time complexity. Um, because there is a sort, right? There is a sort. Um, so the sort there are um n folders. Uh, so and assume there are for every folder um the the length is L, right? So that will be NL log N for this kind of sort. And for our insert, right? So that will be for every if there are L, right? So at least there are L nodes, and so we'll insert N multiplied by L. So the time complexity for this approach is NL log N, and space is O N L, right? Because let's say that the length is also linear, right? So the time complexity is O N L log N, space is O N L. So this is one of the approach. Actually, for this question, we don't need to even use the trap. We can even just use a list to check its previous substring, right? So what we do is that instead of use a trap, we can use a list to do this directly. Let's still sort this kind of folder. And what we do is that we're going to have this string result equals new array list. What we do is that uh, for every string, there in folder, right? So that means that if this kind of result is empty, or after sort the previous one, the last one, right? Only the last one and the current one is possible that that will be its child because for example A B C, right? And if we sort, it will have A B C and for example D just after this. So only um if the previous one can be its parents, so that means um if it's our result for every for our result, if we don't have any prefix, right? For example, AB, and when we insert the next one, A, B, C, D, right? If we find in the result any prefix, we'll skip this. If we didn't find any prefix like AB, then we'll add to our result. Then we'll say if mm, ER start with result get result dot size -1. Um, And here we should add an slash here because the reason is that, for example, we have A, B, C, right? And next time we are going to insert is A, B, for example, C, D, E, those kind of things will be skipped. But the things that it's possible, if we don't insert, right? We insert a slash when we insert an A, B, for example, C, D. This will also be skipped, but in this kind of scenario, we should not skip this, right? So let's add a slash to avoid this kind of errors. Doing like this. Only we don't have its parents. Then we're going to have a result. Yeah. In the end, we just return result. Um, Doing like this, let's analyze the time complexity and space complexity. We'll say um, we have sort, right? As we talk about the sort is NL log n, NL log n space complexity, time complexity. And then what we do is this kind of checking is an n multiplied by L checking, right? So this time complexity will still be NL log n, and the space is NL, right? So this is another approach. This code will be very short, right? And if we don't want, let's observe this question. We don't actually what we don't want to. We'll find uh, this sort is kind of redundant operations. Actually, we don't care about the order of the folders, right? We just care that, for example, A, B, C, right? And those kind of A, B, C, D, whether they exist or not, right? So, for example, when we check A, B, C, D, we just want to check whether it's a prefix, for example, A, B, C, it's exists in some data structure, right? So what we're thinking about is that we can put those folder or dir into a set, right? Initially, we put that into a set. Then, for every path, what we do is that we check this whether it's in set, or then check this whether it is in set, then check this whether it is in set, right? If any of its prefix is in the set, then we cannot add to our result. Otherwise, we add to our result. So, so let's use a set way, write another code, right? So we have set string set equals new hash set. So for string dir in folder set add dir. Then what we do is that we need to list the string as the result, right? New array list. So we just write our add help function for string dir in folder. So add. We need this set. We need this dir and result. In the end, return result. So the help function is add, and we need a set string set, right? string dir and a list of string results. So what we do is that we can do 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 this while true int index equals and let's set this initially the index is 0 int index equals 0 and the index equals because the initial one is is 0, right? Mm, we want to skip the first one, right? Dir index O um, from index plus 1, right? So I say if this kind of index equals -1, we should break. Should that means that means the things that we want to check whether this kind of substring um, parent equals dir dot substring from 0 to index. Whether set contains this parent, this one, this parent. So let's say if set contains this parent, then what we do is that we just return, right? For this one, we don't need to add to our results. And if in the end, this index is -1, that means there is no more slash. That means we didn't find any parents in the set. So we'll have just a result add. Yeah, right. So you'll see doing like this, it is much faster. Actually, let's look at the time complexity. The set, uh, let's assume there are n operations. There are n folders, right? DRIs, and each one has length L, or we'll say uh, L is the slash number, right? Because this one, the worst case is slash is the same level as L, right? So this is an L operation. And for this one, this add, this is because we need L times, and for each time we need to check whether set contains this. This is L. So this is L squared, right? So L squared operation. And this is n folders. So this is nl squared time complexity, right? And space is still nl, linear data structure. So let's see, doing like this, it's very fast. And also because this L is small, right? This L should be small because that is at worst case is the folder length, one of the DR lengths, right? That is smaller equal to 100. So doing like this is it has the best time complexity, and the space is ONL, right? I'm going to convert the last two methods into Python code. Only those kind of sort use a list to check the last one, right? And so we'll have folder the sort, And for the child, I'm not a red person anymore. And this one equals this. So for this code, is for dir in folder. Um, in folder. What to say? If not result or not dir start d dot start with start with uh start with result the last one, right? Minus one plus slash then result append d, and in the end return result. So this is a O N L log n. And let's look at the set operation. The using set code. So we'll have folder set equals set folder. And what it is result equals this, right? And what for dir in folder, let's say d in folder. Then we're going to add a folder set and the result and the return result. So let's write a help function that add. We need a folder set, which is set of string. And dir, let's use d, use a string. And a list of result with a list of string. So what we do is that we need let's have index equals to 0, right? So while true, we'll say index equals to d dot find from index plus 1. So we'll say if this index equals minus 1, we'll break and we'll have a parent parent equals to dir. We can from doing like to index from 0 to index. It's a D, right? Not a dir. D. So if a parent not in, if this in this kind of folder set, just a return. And otherwise, when we're jumping out of this while we start append D, right? Okay. This will be O(n)(L) square time complexity in the O(n)(L) space complexity.